Thank you very much, Roland. Thank you very much for the invitation to this seminar, and thank you very much for the nice introduction. So yes, my name is Valentin Bertsch. I'm presenting here, but as I guess is the case for all of you, I do not present just my own work, but there are several people involved. Most importantly, let's say the core part of today's research is by Leonie Klager, a former PhD student of mine. Paul Pitts is the kind of one that is the successor, and that's kind of taking that forward, but there's also many other people involved. Now I want to talk about long-term energy systems planning under uncertainty. Towards the end, I'll discuss deep uncertainty. And I, let's say, want to focus on the example of climate change uncertainty, because I think that's can also be interesting to kind of see where there might be opportunities for collaborating between you guys and what we do in our group. So what I want to achieve with this talk is essentially, I mean, for Christian, that might be rather boring, but for most of you, I mean, if you're more from a, let's say, theoretical, methodological background, maybe it is good to kind of at least get a warm up and refresher of what are energy systems models and how can they be used, how are they normally used for long-term energy systems planning. I would like to provide an overview, just very briefly, of some selected recent advancements that we did in our group on energy systems optimization modeling. And then I'll do like a deep dive and present a case study on how climate change uncertainty can be considered in energy systems planning, give you a brief summary of the state of the art, focus on time series clustering, where I think there might be some interesting opportunities for collaboration, focus on the application of what can we do with those time series clustering approaches and derive some conclusions, and then would like to discuss limitations, future research, and identify potential areas for collaboration. So I'm not sure who has seen an energy systems model before. Who knows what an energy system model is or looks like? One, yes, one perhaps.
Should have seen it.
You should have seen. Never, no worries. So because it's also a question of system boundaries and what do we mean by systems? I'm in a department for mechanical engineering where many of my colleagues also use the word system and they mean something like a heat pump, where when I talk about a system that's normally much larger. So a small system for us is a house or residential quarter, but normally we look at systems of national scale, European or global. So we have a system like the German power system with power generation units, can be renewable or non-renewable. There is grids, there is storage. And of course, it's a model. So we kind of do some abstractions and we collect the real data and we can kind of summarize that in our model, which has sort of a grid structure where we have commodity grids, an electrical grid, maybe a heat grid, a storage grid, and so on. And what goes into the model, there is all sorts of input parameters. We need information on energy demand, normally hourly or sub-hourly resolution, depending on what we want to look at, fuel supply, transmission capacities between different nodes. We need information on existing power plants, of course, that are already in place here, but also on power plants that can be added to the system that might be needed for future, covering the demand in the future. We need information on investment costs, efficiencies, and so on and so forth. For the renewable power plants, we need information on weather time series, which are very important for solar supply, wind supply. So we need information on storages, and there is some additional constraints. What we do with that in the optimization framework is essentially, normally the standard way is we have minimize the total system. So say the objective function is minimize all investment related and dispatch related costs, and subject to some constraints, where the most important one is like an energy balance, which in the end means make sure supply meets demand at all times. You can also put constraints on the model like decarbonization targets and things like that. And then what comes out of that is in the long term, and I think that's what our focus is essentially on, we get information on the technology mix of the future. So under those constraints, what is a cost minimal technology mix and what capacity investments are required demand in 2050 that only has zero emissions, 10% of today's emissions, or whatever it is that we put as a constraint. You get information on fuel consumption, state of charge of the storages over time, use of transmission lines, need for new transmission lines. We also have some derived outputs, like what are the overall emissions. Proxy for market prices are like the marginal cost of the system that we can derive, and hence we can also derive market revenues and things. And what do we normally use them for? We normally use them for things like, let's assess what is the demand for energy storage, for different energy storage technologies in the future European power system. And then we have we can choose different nodal representations. For guys like Christian, that would be a very coarse spatial resolution, because essentially, with the exception of Germany, we have one node per country in this model. And of course, if you're interested in detailed grid studies, you need much more nodes, but that is more or less generic. Here we have a rather coarse resolution, one node per country, essentially. And for each node, we can then look at, okay, what's the demand, what supply options do we have today, and what do we need to invest to kind of decarbonize overall in the long run. I think I can go over that rather quickly. So that's just a more detailed objective function, but essentially that's all the kind of variable generation costs, the fixed operating and maintenance costs, and the investment related costs. And there is some penalty for unserved energy and investments into transmission lines. And you have some energy balance constraints, so meet demand at all times. And in the units, how they are called in the system, we normally have some energy conversion, where information like the efficiency and heating value of the technology and so on and so forth are used and converted to kind of mathematically describe the energy. And what comes out of these models is then in the long run, let's say in this study, as an example, if we don't decarbonize at all, that's the left-hand side, increasing decarbonization until C100 means we remove 100% of the CO2 emissions. What would the future system look like for the European system that you have just seen? What's the different generation technologies? And we can also look at what capacity investments are required in different technologies, in different storage technologies. Here, just for illustrative purposes, we have looked at pumped hydro, lithium-ion batteries, vanadium redox flow, compressed air, and hydrogen. And that's pretty much in line, let's say, with the majority of studies on need for hydrogen, for more generally for long-term storage, for decarbonized systems. We can really achieve up to 80% without any significant long-term storage investment requirements. But once you want to move from 80 on to 100% decarbonization, at some point to get over energy droughts and so on and so forth, you need more long-term storage. Okay? That's just like as a warm-up what normally we mean by energy systems models and what we can do with them. And they used for decades to essentially provide support to decision makers in governments, so for policymakers. Also, companies use them. When I work with EnBW, we have used very similar models to kind of support investment decisions and derive like long-term planning scenarios also for the company. But of course, there is lots of uncertainties, because if you look at all the input side on the left-hand side, essentially, if we do long-term studies out to 2045 or 2050, do we really know what the energy demand is? Do we know what the transmission capacities are? Do we know if today's technology costs will be the same? Sometimes technology can become cheaper, sometimes they become more expensive. What are, especially weather, also highly uncertain. So lots of uncertainties, and that's what we normally summarize as parametric uncertainty. Because these are the input parameters. But there's also so-called structural uncertainties with the model itself, okay? So do we really only want to always look at cost-min systems? Is that what the decision makers really, is that the one and only objective, or are there other objectives that count? Do we really describe in the model how reality works? So there's also structural uncertainties that are, or require different approaches to handle them. And in the end, in the light of all these uncertainties, of course, we can ask ourselves, do the outputs really serve the intention? Can they really be useful for energy systems planning in reality? And so what can we do, or what have we done in the recent past to kind of overcome some of those uncertainties? Let's say in terms of, I mean, this part is, say more about the structural uncertainty or structural limitation. Is it always only about cost minimization? Of course, we can also introduce multi-objective optimization, like the Okamekana approach that can be easily implemented in energy systems frameworks. I'm sure some of you have heard about that before. Essentially, you derive a Pareto front rather than a point estimate, rather than a point optimization, where you have infeasible solutions, you have suboptimal solutions, non-optimal solutions, and in the end, basically, by using the Okamekana approach, you determine the boundaries. You can then decide on a desired number of caps, basically discrete points in between the boundaries you have determined in the first step. And then you solve the above problem for each cap. And the nice thing is that you can parallelize that third step and that kind of speeds up that optimization process. So by that, you can look into, now you don't not just limited to looking into cost minimization, you can explicitly look into emission minimization, not just put a constraint on that. You can also look at self-sufficiency or whatever, maximization. You can do all sorts of things and optimize for more objectives. Okay? One way where we have used that is also, going back to the parametric uncertainties, that remember I said all these parameters are usually highly uncertain, and there is a special challenge when we talk about newer technologies. I mean, we don't really know in 30 years from now, will we really need the same technologies that we have in the system today? Maybe some technologies, some storage technologies have not really been developed yet, or are really low TRL technology, low technology readiness level. Okay? And for those very low TRL technologies, assessing costs, future costs, what they might cost and how efficient they might be in the market is incredibly uncertain, if not possible at all to quantify. So what we thought about, let's turn that around, use multi-objective optimization to kind of turn what was traditionally an input parameter into the variable of the system. And so what we have done essentially is we have, for the example, this is a Carnot battery. For those who don't know that, a Carnot battery is power to heat to power energy storage technology. That is rather low TRL, and there is a priority program funded by DFG where we are a part of that. And let's say we have applied that idea for the Carnot battery using the CAPEX, so the specific technology cost of the Carnot battery as an optimization objective. So what we then do, of course, we still have the total system cost also as an optimization objective, because otherwise, if we don't do that, really off reality, we can then kind of identify market entry levels for what is the maximum CAPEX that the technology can cost to have a room in the system. Okay, so a very, let's say, an approach that helps us to identify or provide guidance for technology developers and kind of circumvent the fact that we have very high uncertainty in terms of the technology cost. Another approach that is getting more and more traction in energy systems modeling is modeling to generate alternatives. This is essentially another reformulation of the optimization problem, and I'll get back to that at the very end. So again, it starts off with a single objective minimum. So say we do the cost minimization of the system. Once we have obtained that, we decide on how much more cost are we willing to allow, say maybe 5 or 10% more than the cost minimum. And then we get what we call a near optimal solution space. We can identify a number of diverse solutions within that optimal solutions. That's especially relevant because what many people that just are users of energy systems models don't really realize that the objective function near the theoretical optimum is typically very flat. Okay, that means you have a huge choice in variable space with minimum impact on the objective. And that kind of means that you have lots of different alternative systems that you can build that are almost identical in terms of the objective. And in the light of all the uncertainty on the input side, I would say they're not even 2% more expensive. They are equally expensive in the light of the uncertainty. Okay, so that's modeling to generate alternatives. Here we start by obtaining a single objective minimum, and we decide on, let's say, some slack, some accepted extra costs, and then we can derive those near optimal alternatives. And we have done that and wrote a nice little paper on applying this method. We implemented it in our energy systems model, and we applied that to our university system of RUP. Okay, so that's our university energy system, mainly heat supply options. So what can we take from that? So basically, these are different technological options: low temperature heat pumps, high temperature heat pumps, geothermal, data center as a heat provider, pellet boilers, biomethane boilers. And you can derive, okay, from within that 10% cost range, you can derive like must-haves. Okay, you see geothermal power plant or heat provision is part of any single solution within that 10% cost space. Whereas biomethane boilers, you have a real choice. You can build systems without or with really a lot of capacity. So it kind of helps identify a diverse set of solutions. And Also, sometimes you may be not satisfied with the, let's say, cost minimal system that can be built. So say we want to move from some fossil system, we have a cost minimizing model, and this model suggests us that we should decommission some of the fossil power plants, we let some in the system build a bit of wind, simply speaking, and we're not really happy with that, okay? So modeling to generate alternatives can help us kind of create a set of diverse solutions and say, okay, you can get a really cheap system, but maybe for just a bit of extra money, you can get this solution or that solution, and you open up the solution space, okay? So far, so good. So that's kind of the approaches to deal with uncertainty that we work on a lot as a group. You may be asking in the end, okay, the guy said uncertainty in the title, and he's not at any single slide talking about probabilistics, about probability distributions or stochastic optimization. That's, I mean, you can do that for the mid-term power systems planning and short-term power systems planning. There's all sorts of stochastic programming that's going on, and that's very important, relevant for the operational side. But for long-term planning, I would argue that normally we know too little about the probability distributions to really be in the position to use stochastic programming in a reasonable way. So we prefer to work with methods like the inverse approach that I presented, or with modeling to generate alternatives. And that said, I'll come back to some of that towards the very end. I would like to jump into the example of climate change uncertainty. And let's say the central question of this case study that I want to present is how can a low carbon European electricity system for 2050 be planned to maintain high levels of security supply under climate change uncertainty? So just once again, that picture, we're essentially looking at, I mean, we're not ignoring all the other uncertainties, but just as an example, we're looking at that weather input here. And let's say the observation is that the majority of existing research in energy systems modeling either ignores that fact altogether, that there is uncertainty, or uses historical weather data only. But there's only very little research that looks into, okay, if more and more of our systems, power systems, are based on renewables, they are heavily depending on the weather situation. However, climate change might have an impact on weather patterns. So we should actually be concerned about, does it make sense to historic weather data as an input, or should we move on to trying to combine in outputs from climate models? And that's what this is about. And just to say one more word, it's not just the renewables. If you look out there in reality this week, for instance, or last, it's not just the renewables, it's also thermal power plants that are heavily affected by weather patterns, because they require water from rivers for cooling thermal power stations, and there are constraints on withdrawing water from the waterways these days. And so it's thermal. We observe that in France every summer with all their nucleus. So there's thermal power plants, nuclear power plants, line ratings. I mean, also the transmission line capacity is temperature dependent. So if we know weather will change as a result of climate change, we should try to incorporate that into our models. Okay? So to kind of substantiate that hypothesis that there is not so much research going on, we did a literature review looking into 160 research papers in that space, and we kind of split the literature we found into two large areas. One essentially being, how can we convert climate model output to energy systems model input? So climate models essentially produce outputs like, I mean, each of climate variables. So you can get for various different, let's say, carbon emission scenarios into the future. So carbon concentration pathways for various different assumptions on that. You can get information on what do we expect in 2040, 2050, 2060? What do we expect? How do wind speeds change over time and in a spatial resolution? How does solar radiation change? How does precipitation change? How do temperatures change? All those sorts of climate variables. We can get that from climate models as an output. And we basically found there is not so much, I mean, the methodology is pretty clear. How could you convert that climate data into energy systems model input data? But there were not really any tools that can automate that and kind of allow you to do that sort of analysis at scale. So what we did is we developed an open source energy system, open source small tool providing input data to energy systems. So basically downloading automatically from the Cordex, as it is called, the Euro Cordex data set. Eurocortex is essentially fine resolution, a grid across Europe with 12.5 by 12.5 kilometers. That's the spatial resolution. And it provides data out to 2100, I believe, on what are those climate variables in different climate scenarios, how do they develop over time. And also Eurocortex does not host one single climate model, but they host a number of different climate models. So you also can look into what does climate model 1 say, what does climate model 2 say, and so on and so forth. So you have different climate models, different emission pathways, and for all those different models and emission pathways, you can get an idea of reasonable developments of those climate variables into the future. And with that tool, we can then translate them into series of energy input data. And the second part of literature review was basically, okay, how are these different climate scenarios that we can get out of the climate models, how are they used in energy systems models? And what was really interesting for us and a bit surprising, that there were some studies that claimed they looked into climate change and how that impacts the energy system, but most of them essentially then picked a scenario. So that one single scenario from a climate model, putting that into the energy. And the other side was what I mentioned before. There are some people that claim they analyze weather uncertainty and the impact on the energy system, but they purely look at historic weather. But there was not really much going on in that kind of intersection where you try to look, okay, what's the climate uncertainty, and put all the climate uncertainty and the impact on the weather variability into the energy system. And of course, there are also good reasons why that is not so easy to do. Because if you look at, it does not make sense, does not make sense to just look at one future year, but there will, as in the past, in the future, we expect there will be intra-annual or inter-annual variability. So will be different weather years. There will be different climate models, and none of them is wrong or right, but they just have different strengths and weaknesses. And there is different RCP scenarios, representative concentration pathway. That essentially means, so do we aim to, or do we manage to stay within our Paris Agreement, or do we shoot above it, and how much do we shoot above it? So it's basically how does the CO2 concentration in the atmosphere develop? We look into different climate models, different years, and different RCP scenarios, and we want to put all that into our energy system model. Then normally what we see is model will blow up. We can't handle all that data at once because the computation is complex too hard. And that's essentially the starting point for, and that will be interesting what your ideas are on that, for we need some time series clustering. And we did try out a whole lot of things, and I'll take you through some of the outcomes and findings of that. So we did time series clustering to kind of make that manageable and use all that data in our models. So I think you know more about time series clustering than I do, but in the end, the idea is we want to kind of start with a longer time series of length n and make it shorter, reduce it to length k, okay? And there's many different methods out there to do that, of course. And the typical methods don't really focus, because I mean, in the end, we want, when we do that, we want to make sure that we kind of pick or don't reduce the wrong points in time that are relevant for the systems design, because in the end, we would still to maintain the security of supply in the long run of this. And the clustering methods typically don't have a strong focus on security. So what we came up with, or in particular, the research with Leonie Klager, who I refer to on the title slide, is we developed a new clustering algorithm called optimization-based priority clustering. And it basically combines different aspects. I mean, the name kind of gives away what it is. It is optimization-based. It's priority. And what is that? And it combines JSON cluster. So there's 3 different methods that we kind of combine into that new OVPC method. JSON clustering basically looks into, and I have an example on the next slide, basically conserves the chronological order, and essentially by conserving chronological order tries to kind of combine two neighboring time steps that are most similar and then moves on to the next. Optimization-based clustering is very different from the others, because adjacent clustering you normally do on input data. Optimization-based clustering you do on the output data. You first run an optimization using your energy systems model, and then based on that finding, some clustering. Downside, of course, is may have some computational disadvantages. You need to run your model at least once to produce that output, but still might help you then for further calculations. And priority assignment is essentially, you can use different indicators for the priority assignment. You can use the system costs or loss load or something like that to kind of give certain time steps, certain parts of your time series a higher priority than others. Okay, we kind of combined all these three methods into one and call that optimization-based priority clustering. So how does it work? Take as an example, you have a time series like this. First of all, you divide it into day-long time slices. Then we optimize them. We optimize these daily time slices individually. And then imagine you get results. This is installed capacity, and here are the costs, wind, solar, battery, and hydrogen, and what are the costs. And that's the optimization-based clustering. So you optimize them individually, but you can parallelize that because you optimize the individual days in parallel. Then you look at the costs, and you can use the costs as a priority indicator. So you assign very high priority, high, and normal priority. And then you can remove the cost from this, and essentially then comes in the adjacent clustering. So essentially it works like you look at the Euclidean distances, which if you look at those different times, days, one after the other, basically combine these two because they have the smallest Euclidean distance, and essentially then merge them. And then there is different ways how you can merge them. This would be like as you see in the example, that was the arithmetic mean, but we normally distinguish then depending on if you have 2 days with very high priorities, we don't merge them at all. If we have 1 day with very high priority, another one without high priority, then we would normally take the one with a very high priority as a new element. And if we have 2 that are not, and none of them is very high priority, then we take essentially the arithmetic mean. Okay, so it combines those 3 elements. And then how do we measure that clustering performance with respect to security of supply? We basically do the investment optimization, which is computationally most complex. We do that with a cluster time series. Then we run dispatch optimization with a full time series to kind of analyze, will the model really in 8,700 hours be able to cover the demand at all times? And we measure the lost load. So what comes out of that is we, as a benchmark, we also introduce as an input-based clustering technique k-means. We have the adjacent clustering, which in itself is also an input data-based clustering approach. And then we did the optimization-based priority clustering with all sorts of different parameterizations. And what you see here on the right-hand side, so within that set, not all of those parameterizations are better, but you see that the loss load on the x-axis, especially the k-means and also the adjacent clustering, are not really performing so well. But we do find parameterizations where we can get really good outcomes for reducing or minimizing loss load with optimization-based priority. So how we normally do that is we use the investment results for the clustering, then we use the daily system costs for priority assignment, and we can also improve the security of supply by increasing the number of days with very high priority. Obviously, increasing the number of days with very high priority also comes at a cost, because normally that means that you can't really reduce the time series so much, but that is like it. And what we found is that we can reduce around 99% of lost load with a rather short computation time using this algorithm. And now we have kind of taken that algorithm to more, let's say, more comprehensive application and benchmarking study on the European power system. So this is more or less similar system that we have seen in the introduction, where I've presented what energy systems models are. So we have the European power system again, and we basically look at a completely decarbonized system into the future. And what sort of technologies do we need? How much solar and wind do we need? How much storage of which kind do we need? And so on. On the climate uncertainty side, we considered for this study 6 climate models, 3 different or up to 3 different RCP scenarios, and 3 years to kind of consider the weather variability years. So altogether, that's 36 years of input data. And we then use that GTS tool that I presented in the beginning to kind of convert those climate variable outputs of the climate modeling world into energy systems modeling input data. And before we kind of get into the results and findings of what we learned in the energy systems modeling, what does that mean? What does the input side look like? So this is just the input side on the relative change in full load hours of the different renewable generators for those 36 different years. And that's pretty similar, I would say. That's it. Qualitatively, that's similar with our observations from historic weather years. We have rather limited variability for solar power. There is much less variability than for wind, for instance. And for wind, see it here, and for offshore wind, it's yet a bit more. Interestingly, for electricity demand, we see a rather low variability between, so low relative change in demand, and the highest change we see with hydro inflows. Also that, I think, is not the biggest surprise, but it's nice to kind of put numbers. And now we kind of compare that with 3 different methods, let's say, for using the data in energy systems modeling. We did single scenario analysis because that's more or less like the state of the art. What if you pick an average scenario or the worst possible of those 36 scenarios? What happens then? We then used our OBPC method that I introduced. And as a benchmark, as another benchmark, we use the decomposition approach. So rather than clustering the time series, you can also decompose the problem. And essentially, I mean, you just as well think about some Bender's decomposition. This one converges faster. I mean, normally it produces, it's more based on robust optimization, I would say. It produces rather expensive solutions, but it converges much faster than Bender's position. And it basically decomposes the problem into an investment stage and a dispatch phase with several iterations. And it's called column and constraint generation algorithm. I thought in the interest of time, I'd skip the details, but we can discuss that later. And now what comes out, what can we learn from that? So for those single scenario analyses, time series clustering and decomposition approach, what you see here is that's the different, that's the average single scenario. That's like the worst case single scenario. So when you plan with a worst case single scenario, this is different OBPC approaches where VHP stands for very high priority. So that's the number of very high priority days in your time series. And of course, as you expect, normally, I mean, it's not linearly, but if you increase the number of very high priority days, you can expect that the loss load is decreased. And the last 2 here are the current and constraint generation outcomes. And what you see on the y-axis is the loss load. So you plan with one scenario, and you get, when you then do the dispatch, you get really a lot of loss load. You can reduce that loss load with both with benchmark, the column and constraint algorithm, and also with the optimization-based priority base. So the good news is we can enhance security of supply with both of these speed-up methods to account for the climate uncertainty in our energy systems planning. What else do we find? If we look into the optimization results, these are different technologies. So we see for bigger differences in terms of biomass, so basically dispatchable renewable generation, we see that the column and constraint algorithm does not really find any biomass investments, whereas some of the OBPC clustering do come up with quite decent capacity in biomass. And with respect to on-wind, so that's onshore wind and solar, we see that there is much less variability, but you find that there is slightly higher investments in wind for the column and constraint than for the OBPC, and vice versa for the other. It is quite interesting also to look at what is the difference in terms of storage investments. I mean, we have seen in the introduction that long-term storage certainly is very important as we move towards very high levels of decarbonization. What we do see is, starting from the single scenario analysis up to the optimization-based priority clustering with many high priority days, is that we see quite a steep increase in hydrogen storage that is needed to maintain security of supply. Interestingly, for the column and constraint algorithm, that is not so much the case. So we kind of stop here at around 50 terawatt hours rather. So sorry, that should not be terawatt hours, that should be gigawatt. Sorry. But we see that there is much less investment in hydrogen storage, but on the other hand, more investment in short-term storage using that algorithm. I'm not sure how I'm doing for time. I'll maybe do this very shortly. So here we compare the, let's say, the lost load abatement cost. So what does it cost you to kind of reduce lost load? And also there, we can find that we have rather low lost load abatement costs for all sorts of OBPC and also for the column and constraint. Let's say with the optimization-based priority clustering without any very high priority days, we even find negative lost load abatement costs on the right y-axis. So that means you can build systems that are better suited than using that extreme single scenario case with optimization-based priority clustering. And you can build systems that have both lower system costs and lower lost load. And of course, otherwise, the more lost load you want to avoid, that will come at a cost. But we certainly find, and I think I'll get back to that, that let's say the bottom line is the lost load abatement costs are lower than the values of lost load of the literature. I think I'll skip that. Let's say the one thing that I would like to emphasize is that if we compare, I mean, we find that the lost load abatement cost between the optimization-based priority clustering and the column and constraint generation algorithm are more or less comparable for these two algorithm configurations each. But what we do find is that indeed, for the column and constraint generation algorithm, we can reduce loss load even further than for the optimization-based priority clustering. But on the other hand, we find that the computational complexity is longer. So computation time in seconds is longer. And you also see why that is. The CC and CNCG algorithm, basically is an iterative approach, and you more or less have the same amount of time that you need to invest to kind of arrive at the next iteration. And it also increases security of supply from iteration to iteration. So after 4 iterations, you end up having much more computational time that you need to arrive at a solution than for the OPPC. But the OPPC is less affected by iterations. You have some initial investment, that's what I mentioned earlier, into the OPPC because you have the pre-processing. But after you have done the pre-processing, it runs rather efficiently. Finally, on that case study, I think that's very interesting also in terms of, okay, what can we do in the long run? And I think, Christian, we discussed that already over lunch. There is some agreement, let's say, between all these methods. So you find that regardless of which algorithm and method exactly you use, we find more or less agreements in terms of we need more than 1,000 gigawatts in onshore wind capacity. We need around 400 gigawatts of solar PV capacity. And I mean, the absolute numbers don't really matter so much because, as I said in the beginning, they might be driven by what are our technology cost assumptions for wind and solar. But this sort of agreement basically gives you also an indication of what could be robust investments that we can start investing, start bringing on the way, and kind of discussing further details later on. So concluding this part, intermediate conclusions, security of supply can be threatened by climate change. Impacts of climate change are not really well assessed in the literature on energy systems. Hydropower is most affected by climate change. Long-term storages are important for security of supply in a highly decarbonized Europe. And single scenario planning leads to low security of supply. So the uncertainty needs to be assessed with adequate methods. Time series clustering and decomposition approach can both improve the security of supply. There is a trade-off that we found between, let's say, low cost and computation time. More investments in one algorithm in hydrogen biomass and the other more investments in solar, wind, and batteries. High level supply. The lost load abatement costs in all cases are typically lower than the values of lost load from the literature. So that is also an important indication, and all methods agree on around 2,000 gigawatt of installed capacity. Just a few more notes on how are we taking that further at the moment. We have an ongoing research project with Paul Pütz, whom I referred to on the title slide. So here, let's say we look into different storylines. What is a storyline? That's potential transformation pathways of the energy system. So let's say we have a storyline, we want to build a system that's mainly based on electrification, and maybe another storyline is we have a system that looks into or that foresees a system with more hydrogen as part of the solution. And of course, if you have lots of wind in your storyline, then you heavily are depending on wind speeds and maybe not so much on solar. And if you have a system that is built a lot on solar and less so on wind, you're more depending on solar radiation and less on wind speeds, and you also have the hydrogen. Okay. And in that project, we explicitly distinguish between those storylines, which are, okay, how do we expect we want to achieve our transition? And we distinguish that from external events that we kind of then subsequently kind of analyze the impact of external events on that system we build in a certain story. And here we distinguish between events caused by natural laws. So what are these? Like extreme weather events, for instance. And that goes beyond what I've presented previously, because we do not just look into climate change impact under what I would call normal operating conditions, but how does climate change have an impact on so-called energy droughts? Because energy droughts are basically events that we also know as Dunkelflaute or any other sort of extreme events where let's say, does the frequency of those extreme events change because of climate change, and how does that impact the security of supply of our energy? But we also consider societal or geopolitical events like geopolitical shocks, price shocks, and so on and so forth. Okay? And so why do we do that, or what are the main research questions here? We are interested in, does the number of lost load events increase with ongoing climate change, or how does it differ between different climate scenarios or climate models? Are there certain storylines or certain transformation pathways that inherently lead to more or less lost load events because maybe hydrogen helps against lost load events or whatever it is? And do the same weather events trigger lost load in different storylines? So are there maybe points where we need to watch out for? Those are the key events that we need to kind of prepare for. And that's the case regardless of all the weather events and all the different storylines. So that is pretty much work in progress. So what we have done, and just to give you an idea of what we are up to, we do some planning based on historic years in this case, and say just for illustrative reasons, we have that electric and a hydrogen-based storyline. We do investment planning based on those storylines, and then we take like around 120 forex scenarios. So we have the years 2045 up until 2055 for different climate models. And then we do dispatch runs based on the systems that we have designed in the investment stage, and then identify what are the lost load events. And then we can compare that. How much lost load do we find for each storyline? Is the same lost load event critical or the same weather event critical across all the storylines, and so on and so forth? I'm not going into the details here, but this is just for one. It's the planning based on 2010, and just for one climate scenario, then we might find that, okay, in February, there is a point in time when we have some lost load. And that needs to be, or at the moment, we are doing lots of calculations to kind of identify, are there many, let's say, for all the 120 forex scenarios that we look at here, how is the lost load distributed across the year, across all those different scenarios, and to derive, is there maybe some critical points across all storylines, and so on and so forth. So that's work in progress, where we kind of try to look more into extreme events as a result of climate. I would now like to kind of wrap up, basically highlighting limitations. So what did we do or did we not do when it comes to the conversion of climate data? We only looked at one type of wind turbine and one PV cell. Of course, there is heterogeneity that can be we found that the impact of climate change is strongest on hydroflow, but our hydro modeling is rather coarse, I would say, not very detailed, and demand regression is also quite simplified. We have a limited number of years, so yes, we basically looked at 3 different weather years in the future. We can expand that, and we have a rather coarse spatial aggregation, while the coordinate data itself is on a 12.5 by 12.5 kilometer grid. As I said, we have more or less like a 1 node per country resolution. So also that can and will need to be increased depending on what you want to look at. But again, it comes at a cost of increasing complexity. We only looked at a limited number of clustering and decomposition approaches. So also there, I'm interested in what your ideas are, how we could, what further ideas you might have on reducing computational time without reducing information in the time series that we put into the model. We mainly looked into cost minimization models and only consider climate uncertainty in this core part of the presentation. And of course, there's much more uncertainty. And pretty much that work still follows what I would call a predict and act paradigm. So we still try to assess what comes out of the climate models. And we still pretend we know what climate change may look like. Okay? And is that really the case? Do we know what climate change looks like? Do we trust the climate models really get everything right, or are there other unanticipated things that are going on? And especially when we look beyond climate change, I'm sure we can all agree that there are many things where we don't know nothing. And that's the discussion about deep uncertainty. So where we kind of don't really know anything, or at least not sufficiently well, about the probability distributions, and we have only very scant knowledge about a range of possible outcomes. I think it is true for climate change, despite the existence of climate models. It's certainly true for geopolitical distortions. If you think back at what happened in the past 5 years, if I had told anyone that 10 years ago, they would have kind of called me crazy, for sure. When we think about gas price shocks and so on and so forth that we experience. So also here, it's very hard to work with probability. There might be societal attitudes that play a role in complex systems like the energy system. We can have system outages of whatever sort of event, terrorism, cyber attacks, whatever it is. So basically, in the literature on decision-making on deep uncertainty, there's a recommendation to shift towards a monitor and adapt paradigm rather than a predict and act paradigm. And the question is, okay, and what does that mean? What does that mean for future research needs? The MGA I introduced in the beginning, I think, can play a role and can be useful for decision-making under deep uncertainty. And if you remember what I said, basically, we calculate theoretical cost min, we allow for some extra costs, and then calculate a set of diverse solutions. And a part of the algorithm, we need to define a diversification criteria. Normally, we do things like, okay, you want to diversify in terms of technologies, diversify the mix of solar versus wind or whatever it is, or diversify regionally between different countries or within countries. All that can be done. Maybe we need to come up with new diversification criteria that can be related to the adaptability. And then the operationalization of adaptability in itself might be challenging and interesting to look into. But also for me, it's interesting to understand, okay, what are the requirements for selecting climate scenarios? Because it doesn't mean we don't want to work with climate models at all anymore, but what does it mean for the different climate scenarios and which ones I select? And what does it mean for data analytics and data analysis more generally? Finally, and now it's nice that Florian is in the room, for the realization of the energy transition, ultimately, we will need, I presented more or less like the central planning perspective. Ultimately, we will need private investments. Okay? We live in a liberalized system with private investments. So that means price profiles of the future are inherently important. I said in the beginning, we can derive price profiles from our models. Yes, and Florian does very different methods to derive price profiles. But I think what is challenging here is that if you remember and the market, how they work, is the prices, the power prices are basically a function of the underlying physical power system of the technology mix. Okay? They determine what prices we have to a large extent. We know the system itself is changing, but how exactly it changes is highly uncertain. And the environment of the system is changing and uncertain. What does that mean for deriving reasonable price estimates for the future? And do we know anything about price and risk variability in space and time? So will the price variability be the same in France or in Germany because they have different regional energy strategy? And will the risk associated with investments hence be the same across space and time? So also that can be very interesting and can be maybe topics of joint interest. And more generally, I think handling and increasing model and system complexity, any approaches here can be useful. So any other spatio-temporal time series clustering approaches based on input or output data beyond what we have tried, certainly there is much more to do. Further approaches to deep coupling investment and design planning, and on the other hand, dispatch planning. For instance, we are trying out some approaches where we can use like an energy system optimization model for the design phase, but then use some machine learning based approaches for the dispatch to kind of speed up things. How can we combine that? But then again, it's interesting, okay, how can we provide training sets for the machine learning for future power systems that are different from those that we have from the history? So we can use model outputs for the training. So there's lots of things that I think can be interesting to do in the future, and maybe some of that we can do together. I look very much forward to your questions. Thank you.